All right, ladies and gentlemen, today's class recording has started. So, up on the board is a picture. Just to kind of give you the background so the video has it, right? The next week, next week or two, we are going to look at applications of Newton's second law and Newton's first law, how it applies to different situations. So we're still going to discuss the concept of inertia, net force, acceleration, and the factors that affect that acceleration, but now we're going to apply them to some specific cases. So we're going to start off and talk about friction, because it's a force that affects motion that we have all the time, so it's important that we understand it. So that being said, up here, number one, it says a crate filled with delicious junk food rests on a horizontal floor. Only gravity, only gravity and the support force of the floor act on it as shown by the vectors for weight, W, and normal force, N. First, what do we call this picture on the left-hand side?
Diagram.
What kind of a diagram? A free body diagram. All right? A free body diagram shows us the forces that are acting on an object in a situation. Okay? So in this case here, like we've discussed many times, an object that is sitting motionless on a surface has two forces acting on it, right? What are they? Gravity what? Gravity down and the surface up, okay? So gravity is sometimes called weight. We'll learn that a little bit later on this week. And then the surface is generally referred to as the normal force, all right? So weight is this downward force right here. Normal force is this upward force right here. If this object is at rest, as it says in the description, what has to be true about it? Joe? The net force on the crate is 0. Joe, what is your evidence for that? It's motionless. That's true. Let's go something a little bit more, right? There's something else I want you to say.
There's two equal forces acting.
How do you know there are two equal forces acting on it? It's motionless, which means it's not what? True. It's at rest. It's not accelerating, right? An object that is motionless is not accelerating. So if we're going to say that the net force is 0, our evidence for that is that there is no acceleration. Good there? Good with that? Okay, so we want to move the crate. It says a slight pull, P, is exerted on the crate, but not enough to move it. Okay? So here, when we did our lab from last week, there was a question very similar to this in the analysis part. Okay? If you pull on an object and it doesn't go anywhere, a lot of times our first instinct or our first explanation for that is what? It's too heavy. We're not pulling hard enough, right? But that sort of speaks to the object's mass. Does mass determine if something moves? No. What determines if something moves? Net force, right? Mass helps determine how much it moves, but not if it moves. Okay? Is that good? All right. So, can the explanation for why something doesn't move ever be that it's too heavy? No. If something doesn't move, what has to be the explanation for it? Well, net force is what? 0. If something doesn't move, the net force has to be 0. Always, always, always. Okay? Now, taking it back to this picture right here. The person in the picture has pulled, but it doesn't go anywhere. There were 2 forces in the previous picture. Now there's 4. right? The pull to the right, and which other force has shown up? Friction has shown up, all right? Notice, there's no friction in this picture. That's important. We'll talk about why when we get into the outline a little bit later on, okay? So, if we have these two forces and still nothing is happening, what does the net force have to be? 0. So, a friction force now acts, which is, how does that friction force have to compare to force P? It's got to be equal to. Okay? Has to be, has to be, has to be, because now the net force is what? 0. And you still have no motion. Okay? All right. Good there? Okay. The next one is a little, oh wait. So, if we pull with 150 newtons and that crate doesn't move, what has to be the magnitude of F? 150. Well, so what is the question asking you for? The magnitude, right? And magnitude only tells you what? How much, right? So if we're talking about, it would be speed if we're talking about how fast something is moving. But more generally, magnitude tells us how much, right? What direction does F have to be going? Opposite of P, right? So that when we add them together, we get 0. Okay? Oh, sorry, that was question number 5. Yeah, we're gonna come back to 3 and 4 because they're different situations. So, if you pull on an object and it doesn't go anywhere, what's your next plan?
Make it go somewhere.
Well, in order to do that, what are you gonna do? You're gonna pull harder.
Figure out your life.
Right? Okay. What?
Figure out your life.
Well, maybe.
Break it and move it.
Wow. So, the pulling force P increases now to 200 newtons. This is number 6 on the product. And the crate still doesn't move. What had to happen to the frictional force? Had to increase as well. To what? 200 newtons. Because if something isn't moving, the net force has to be what?
Equal
0.
He doesn't want to hear these
That's not happening.
He doesn't want to hear he's pulling very hard.
Well, you know.
Yeah, it says.
Who are you to judge how hard he's pulling, Edie? All right. Are we okay there? Okay. The next question can be a little confusing. Okay? So, it says, the pull is increased until the crate begins to move. But that's not what this question is about. It's not about the crate first starting to move. It's about the crate that is already moving, and like it says, pulled so that it moves with a constant velocity across the floor. Okay? So this crate now is moving with a constant velocity across the floor. It's not the instant that it started moving. It's after it's already been moving, and now we're sliding it across the floor, constant velocity. Okay? All right. What are the key phrases in the section, or what is the key words that I highlighted in the yellow section? Well, sorry. What are the key words within the highlighted yellow section that you need to help answer this question? Constant velocity. All right? Joe, if something has a constant velocity, what does that mean? Correct. Is it moving? Yes. Is it accelerating? No. If it's not accelerating, what has to be true? The net force is 0. Not necessarily can't be the friction, right? Okay. The net force has to be 0. Even though it's now moving, right? The net force has to be 0 if we're talking about constant velocity. Okay? Don't get tripped up. This isn't the moment when it starts moving. It's already been moving. Now it's moving with a constant velocity. Okay? Like this. So if I just do this, right, move this book with a constant velocity across the table. Not at the moment that it started moving, not at the moment when it stopped moving, but at that section when it's moving across the table. Okay? If it's not speeding up or slowing down, the net force has to be what? 0. And the only way for that to happen is for F to be compare how to P.
Has to be less than, or equal to I.
Gotta be equal, right? Because constant velocity means what about the acceleration, Joe?
No, it's 0.
And if the acceleration is 0, what else has to be true?
No.
Net force has to be equal to 0. Okay? Good there? So, one of the other questions from that's a good question. How is it moving if the friction is equal to the pull? Okay? One of the other questions in the lab from last week, right? Objects only move when force is exerted on them, right? And now you had to evaluate true or false. Okay? Objects only move when forces are exerted on them, true or false?
False.
False.
But it'll continue to move unless it's
If we got it moving originally, and then the forces are balanced, what will it do? Stays in motion, inertia, right? To get this car to move, I have to push it. But once it's already moving, do I have to keep pushing it? Right? Because what's true about that? Yeah, there's friction on that track, right? If I want to keep that car moving, what do I have to do? Either no friction, or what else can I do? I can keep applying a force. How big does that force have to be? Actually, it depends.
It doesn't matter. If you want it to keep moving to the end.
Do you want it to keep moving, or do you want it to keep speeding up? Does that make sense? If I keep pushing it more than friction, what will this car do? Faster, 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 faster. If I push it just as much as friction, what will it do?
It's constant velocity.
Constant velocity. Okay? Is that good?
How do you get rid of it?
No, you can't. How's that? You did it? No, no. All right. Question number 7, down at the bottom. If the force of sliding friction, so the frictional force that's acting on this cart, or on this crate as it slides across the floor, is 250 newtons, what force is necessary to keep the crate sliding at a constant velocity? 250 newtons. Okay? All right, good there? So Edie, let's talk about that situation that I just posed to you, okay? Pull P is further increased and is now greater than friction. Okay? Edie, does it look like he's exerting enough force now? I know you were a little disappointed in the amount of effort he was giving back in question number 2. So, right? Back here at question number 2. He's not working very hard, right? But now he's got that thing slung over his shoulder, right? Okay. All right. Pull P is increased and is now greater than friction. What does that mean about the net force? Greater than 0. And if the net force is greater than 0, what's going to happen here? There will be acceleration. Okay? If there is a net force to the right, what has to be true in this picture in order to have a net force to the right? What has to be true in this picture if net force is to the right? The right arrow has to be bigger than what? The left arrow. All right? So if we have net force to the right by P being greater than F, which way will it accelerate? To the right. If this object is moving to the right and it's accelerating to the right, physically, what would we see happening to it? It would speed up. It would go faster and faster and faster and faster. But in this case, the net force is to the right, so acceleration is to the right. Okay? Good there. All right. Let's take this from just a qualitative analysis to a quantitative analysis, right? Let's go from just describing to actually measuring and getting some numbers. The crate has a mass of 50 kilograms. Sliding friction, the friction it experiences as it slides across the floor, is 250 newtons. What is the acceleration of the crate when the pulling force is 250? Zero, right? If we're pulling with 250 and friction is 250, what's the net force? Zero. And if there's zero, that means that there is no acceleration. Okay. Good there. Okay. All right. The pulling force has now been increased to 300 newtons. All right. What is the net force now acting on the crate? 50 newtons, right? You have 300 pulling in this direction. You have 250 acting in that direction. So, Edie, that means the net force is
50.
which direction?
Wait. Left. Right.
Probably right, if
Yeah,
that's, yeah, so, okay.
So you know what?
So, to be fair, he wasn't actually looking at the screen.
I was just so
All right, so now we have an acceleration. We learned earlier in this unit that the acceleration of an object is affected by two things. What are the two things that affect the acceleration of an object? Mass and net force. We put all those things together and we get what? Well, yes. Sorry.
Science.
What law explains and summarizes all of that?
Second.
Second law. Newton's second law. Right? Sigma F is equal to m times a. We said we can also rearrange this equation, right?
So F, no wait, acceleration equals F.
Okay. Acceleration is equal to net force over mass. Okay? Edie,
Yeah.
what was the net force in this example?
50.
50. Edie, what's the mass of this crate?
50.
50. If we have 50 newtons of net force over 50 kilograms of mass, what's the acceleration going to be?
There's no way. It's not 50. It's a joke. I just wanted to say 50.
So,
Wait, one?
do you understand?
Whoa,
Yeah.
50 divided by 50. 50 divided by 50.
Are you okay with this? Or? Okay.
Oh,
so,
the net, oh, I thought it was, oh, why not?
right? The net force is 50 because of this difference right here,
Yeah.
right? But the mass is 50 because of this. So we have 50 newtons over 50 kilograms. That gives us that acceleration. Good? Okay. Last example. The pulling force has now increased to 500 newtons. Edie, what's the net force?
250.
250, right? Got 500 this way, but still 250 this way. So the magnitude of the net force,
It's 500 meters.
so 500 minus 250, so the net force is
250.
250. Edie, what's the acceleration?
What's the answer? 5. Oh, 5. I knew that.
There.
Actually, 5.
Wait, can you tell me how you...
Okay.
It's just 5 meters.
So, do you understand why the net force is 250?
Yeah.
Okay.
Dude, you got burned.
this equation tells us how much acceleration there is based on the net force and the mass. Okay? So, we're in this case 500 to the right, 250 to the left. The net force is 250. The mass is 50. So if we have 250 net force over 50 mass, is that good? All right, good there? Okay. Let's do one definition here, and then we'll call it a day. Okay, so when we discuss friction, there are three sort of key ideas that we need to talk about. One is static friction, the second one is the maximum static friction, and the third one is the kinetic or the sliding friction. Okay? So first, let's talk about friction itself. Okay? All types of friction, no matter what we're talking about, have to oppose something. Okay? Friction is a contact force. There has to be contact in order for there to be friction. Okay? So, Edie, can we get rid of friction here on Earth?
No.
Because as something moves, what does it always run into?
Something.
What is that something else?
Motion. Gravity. Face. Hands.
Air resistance.
That's what I meant.
Okay?
That was my
So even if I hung something like a pendulum in the air and let it swing,
But think of that as
clock it swings back and forth.
Oh.
I have a big maid over there, like I already used the card for it.
So even if I hang something off of here and swing it back and forth, there's still some friction. It's not contacting the table, but it does run into the
What
air.
if you get rid of air resistance?
Okay.
Like in that thing. That big like building.
Yep. Okay.
It's enough for me.
Right. There's, well, okay. So, hey, can you step over the side conversation? So, Edie, if we went into the building and got rid of the air, there wouldn't be any friction as the object fell through the air because it's not running into anything. But if we took like this book and slid it across the floor, would there be friction then?
Yeah.
Yeah.
How?
Because friction is it's a touching, it's a contact force, right? The friction of the air depends on running into the air. If there's no air, we don't run into it. But if there are still two surfaces in contact, there will still be friction even if there is no air. Okay? Good there?
Yeah.
All right. So that's good. Why don't we wrap it up here, and we'll pick it up from here tomorrow. Okay? Oh, hey, real quick, I rearranged the calendar to accurately reflect what we're doing in class. So see here Monday, the friction is up there. There is some reading from the book and one problem that will help you understand what we're doing a little more. We'll get into gravity and terminal velocity tomorrow.